This lesson is 7.1 continued of exponential growth and decay. So today we're going to look at more solving and writing equations. Our learning targets for today is still, given context, I can write an exponential growth and decay equation to model a situation, but I can also solve simple exponential equations algebraically and using intersections on our graphing calculator. So starting off with an example of what we did in part 1, it says the SCIO team at Huntley High School used their microscopes to determine that there is an initial amount of 62 bacteria on the toilet handle in the boys' washroom. Upon further investigation, it is determined that it triples every hour. So write an equation for this scenario and find the number of bacteria on the handle after 3 hours. So what I'd like you to do is pause the video and just get a little refresh with the stuff from part 1 and then play the video to see the answer. So the equation for this scenario would be our initial value, 62, and our multiplier in this case, as we're not adding or subtracting to 100, it says that we're tripling every hour. So it's getting 3 times as big. And if it's getting 3 times as big over the amount of time that we have, that's going to be our final value. So we have y equals 62 times 3 to the t power. So now for b, to find the number of bacteria, on this handle after 3 hours, we would plug in 3 for time, because that's the amount of time that's elapsed. So to find our final value, we have y equals our initial value, 62, times our multiplier, 3, raised to the 3rd power. If we plug that into our calculator, 62 times 3 to the 3rd power, we get 1,674 bacteria after 3 hours. If we wanted to know 7 hours, we'd plug in 7 for t. 20 hours, we plug in 20 for t. And it's going to keep getting larger because it's growth. So our graph would be getting larger over time. And our initial value is 62. So it would be at 62 on our y-axis, that'd be our y-intercept, because that's our starting value. We're starting with 62 and it's growing from there. Another example. It says a physician gives a patient 300 milligrams of an antibiotic that is eliminated from the bloodstream at a rate of 12% per hour. Predict the number of milligrams remaining after 4 hours. So go ahead and write an equation, solve it to figure out how much is remaining after 4 hours. All right, so you would get the equation of y equals 300 times 0.88 raised to the t, and in this case t is 4 hours. So when I plug that into my calculator, I get 179.9 milligrams. So 300 was my initial value. 0.88 is my multiplier that I got from 100 minus 12, because it is decay, so it's being subtracted from 100, and then 4 would be my time. If I showed a sketch of this, it's going down, it's decaying, it's getting less over time, and our starting value was 300, so that would be our y-intercept. But now we're going to get into, well, what if we don't know the amount of time? We know our final value, but we don't know time. How do we solve for this exponent? So all the other pieces we can solve for, but what about this exponent? Well, we've learned about the inverse of an exponential, which is a logarithm, and that is why we've been learning about it, because it's going to help us solve these types of problems. So say we want to solve for an exponent. We want to solve for that time in our exponential equations. We need to use the logarithm because we need to get this x by itself. In order to get x by itself, we got to change forms. So we're given 5 to the x equals 12. Well, 5 raised to any power is not 12 because 5 to the first is 5, but 5 squared is 25. So it's got to be some value between 1 and 2 because 12 is between 5 and 25. But we don't know how to predict what decimal that's going to be. So to find that exact value of x, we need to get x by itself, and to do that we need to change it to a logarithm. So we have our base of 5, so that's going to become the base of our log. So it's going to be log base 5 of 12 equals our exponent. So logs were always equal to our exponent because it helps us solve for that. So x equals log base 5 of 12. Well, how do we figure out what log base 5 of 12 is? Well, we're going to go use our graphing calculators. So go ahead and pull out your graphing calculator, and there's going to be 2 different ways we can look at solving this depending on what type of calculator you have. All right, so on your graphing calculator, if you have a newer version of the graphing calculator, if you have a TI-84 plus CE, or if you have a TI-84 plus or the silver edition, those are all capable of solving this log. So what you have to do is you have to go to the math button. So you want to click math. It's right under that alpha button on the left hand side, under that green button. So if you click math, you want to scroll down to the end of our list, and you're looking for log base. So you're looking for this piece here, log base. If you have this in your calculator, all you have to do is hit enter. And it's going to give you 2 boxes, and where the base is, you plug in 5, and where our next box is, you plug in 12, and you hit enter, and it gives you your answer. So we see here that x is equal to, if we round to 2 decimal places, 1.54. So 5 to the 1.54 power is equal to 12. So if you have that setting in your calculator, that's all you have to do. Math, find log base, and then plug in your base and your other value and hit enter. If you don't, if you have a TI-84, you can download software onto it so you can talk to your teacher about that. Otherwise, if you have a TI-83 or you don't have this function, there is still a way to solve this log. It's called change of base. So to find change of base, you are going to take log base 12 divided by log 5. If you plug this into your calculator, you're going to see that you're going to get the exact same answer. So if I type in log 12 divided by log 5, I get 1.54 still. This is because on our calculator, our log button is always in base 10. So we were essentially doing log base 10 of 12 divided by log base 10 of 5, and that gives us our answer. This has to go into our different log properties, which we don't have at this point. So you're going to take your larger number divided by your base, and that's going to work each time. As we go through more examples, you'll see the pattern of change of base. So here's another example that's in a more similar format to what we've been doing with these exponential equations. So we have 200 times 1.055 to the x power equals 500. And we want to solve for x. So we want to get that exponent by itself. In order to do that, we're going to have to change it to a logarithm. But the first thing we have to do is we have to get this exponential here by itself. But right now we've got a 200 out front, so we got to move that. So we have 200 times 1.055. So to get rid of that and move it to the other side, I have to divide by 200 on both sides. So when I take 500 divided by 200, I get 2.5. So now I have 1.055 to the x equals 2.5. Well, to solve for x, I got to change it to a log. So I have log base, what our base is, 1.055 to the 2.5 equals my exponent x. So I'm going to plug this into my calculator to figure out what x is. So I can hit math, scroll down till I see log base, and then my base is 1.055, and it is to the 2.5. And when I type that in, I get x is equal to 17.11. So if I raise it to the 17.11 power, I would get approximately 500. Now, if I have a version of the calculator that doesn't have log base under my math, then I have to do change of base. So I would have log 2.5 divided by log 1.055. And if I plug that into my calculator, I should get the exact same answer. So it's just going to take learning which way you have to do it based on your calculator, and you'll just go through the exact same way each time. Now let's put it all together. It says you have been given $1,500 for graduation. You want to invest the money in order to make $1,000 on it. The bank is offering a 4.5% interest rate on investments. Roughly how many years will it take for your investment to gain $1,000? So write an equation for your scenario. So let's start with what we know. We know that our initial value is what we're given. So we're given $1,500, so that's going to be our initial value. You want to invest the money to make $1,000. The bank is offering 4.5% interest. So that means our multiplier, we're trying to gain money, so its growth is 100 plus 4.5. That gives us 104.5. So our multiplier is going to be 1.045 raised to, we don't know. So raised to the t power. What we do know in this case is our final value. And our final value is 1,000 more than what we started with. So 1,000 more is going to be 2,500. So our goal is to make $1,000. So we would have 2,500 in the end. So we want to solve for t. How long is this going to take? So we can do this in two ways. We can do this algebraically, or we can do this graphically, like we did back in our intersections unit. So let's take a look at both of these methods. So first, if I want to solve this algebraically, I'm going to take my equation that I just wrote, and I'm going to solve for my exponent, just like we learned using logs. So if I rewrite this, I have 2,500 equals 1,500 times 1.045 raised to the t power. Now I need to get my exponential by itself, so I need to move that 1,500. So to do that, I'm going to divide by 1,500. And when I take 2,500 divided by 1,500, I get 1.666666 repeating. So I have 1.6 repeating. Now I want to save this value in my calculator so that I get a more exact value. Now if you round, you're going to get close to the right value, but it might be slightly off. So leave that in your calculator. And when I divide, this cancels, and I have 1.045 raised to the t power. Now, to solve for t, I need to change it to a log. So this is the base of my exponential, so it becomes the base of my log. So 1.045 to the 1.6 repeating equals t. So now I'm going to go ahead and use my calculator as I had on my prior examples. So if I can, I want to go into math and go find log base and hit enter. Now I'm going to type 1.045 into my base, and then into my next box, if I hit second and the negative button, it says answer right above it, it'll put in 1.66666 repeating, so I'll get an exact answer. And my exact answer would be 11.6 years. Now, if I rounded it slightly, try and put as many decimal places as you can to get more of an exact answer. But you can always hit second answer, which is that negative sign, and it'll put in that exact decimal for you. If you had to do change of base, you would have done log of 1.6 repeating divided by log of 1.045 to get that 11.6 years. So essentially it's going to take you about 12 years in order to gain $1,000 on your initial investment. So that's one way, solving algebraically using logarithms. Now we can also solve graphically because that's something we learned how to do previously as well. Well, if we have two things set equal to each other, remember, we can plug this into y1 and y2. So y1, we're going to have 2,500, and in y2, I have 1,500 times 1.045 raised to the t. So go ahead, pause the video, and plug that into your graphing calculator, and go ahead and adjust your window and find this intersection. Now, if I'm thinking about where this is, y1 is going to be a horizontal line at 2,500. So to see my intersection, I'm going to have to go all the way up, adjust my y max above 2,500 at least in order to see this. So if I go ahead and graph this, I did have to adjust my y max and my y min. So I adjusted my y max and my x max. So my x maximum I went to 20, and my y I went to 3,000. Now if yours was slightly different, you would still be able to see the picture, but you did have to adjust both. Now remember, in applications we're only focusing on quadrant 1, so we're only focusing on our positive values, so we're only going to ever have to adjust x max and y max. We don't have to worry about our minimums. So once I adjust those, I can see I have an intersection point, and remember, to find the intersection point, I hit second trace, and I go down to number 5, which is my intersection. Once I do that, then I hit enter on first curve, second curve, and guess, and it's going to give me my intersection point here. And my intersection point I see is 11.6, 2,500. So 11.6 is going to be my time because this is our x value and then these are our y values. So it's going to be at 11.6 years, just like I found algebraically. So you are going to have to be able to solve algebraically and graphically. So algebraically, we're using logarithms. Graphically, we are using intersection points, and we're finding that x value of our intersection point, which is going to be our time.